Good evening, everyone. My name is Yara T. I've been at Hewitt for 13 years, and I'll be attending Stony Brook University next year for mathematics. And my EI across my 11th and 12th grade years was about using math to model reality. And in 11th grade, I was interested in that idea, but in the context of epidemics. So how, during epidemic disasters, are mathematical models used to describe the spread of disease and determine public health policy? But before getting into that, I think it's first important to establish exactly what a model is. And what all models have in common is that none of them are the real thing. Models are abstract generalizations. They take things that exist and then, using their own unique language, translate them into a simpler form. So thinking about that process in the context of mathematical models, you're taking something that's real and then using math to translate it into a simpler form. So bringing us back to my EI, the question that I wanted to answer my junior year was whether or not these mathematical models, which are only abstract generalizations, whether or not they're reliable enough to be making decisions about public health policy during epidemics. And to answer this question, I went back to the first epidemiological model made. And epidemiological models are mathematical models that are used to describe the spread of disease. And it was created by a mathematician named Daniel Bernoulli in the 18th century in France. And at the time, there was a global smallpox outbreak. And practically every country around the globe, but France, was inheriting the practice of inoculation, which is the fancy word for vaccination. And for some particular reason, the people in France, including very influential figures like the current king at the time and writers like Voltaire, were very against the practice that was spreading to the people, and therefore no one wanted to get inoculated. But Bernoulli saw the benefits in it and figured that he could try convincing the French people of the benefits of inoculation by creating a mathematical model. And in quickest terms, what Bernoulli does with his model is he creates, using math, two versions of the same population, which I call World X on the slideshow. The first version describes the decline of a population living in a world without the threat of smallpox. With the threat of smallpox. The second version of Bernoulli's World X describes the decline of people in that population living without the threat of smallpox. And Bernoulli's goal was to prove that more people will survive in a world without smallpox, which could ideally be achieved with the widespread practice of inoculation. And the results of Bernoulli's model can be described using this table here. The column furthest to the left describes the increase in time. The column right next to that describes the number of survivors over time in the first version of Bernoulli's World X, the one with smallpox. And the column right next to that describes the number of survivors over time in the second version of Bernoulli's World X, the state without smallpox. And comparing the numbers in the last two columns that I just mentioned, you'll see that more people will always survive in the state without smallpox than in the natural state with smallpox, therefore proving Bernoulli's claim about the benefits of inoculation. And there are great things to appreciate about Bernoulli's model, the first being that it proves the efficiency of mathematical models. Bernoulli was able to describe an incredibly complex idea, the spread of disease amongst humans, but using very simple math. He was using calculus that Hewitt students are currently learning at Hewitt. But there were also downsides to Bernoulli's model. And critics pointed out that he generalized reality too extensively in his model. So much so that his model's results no longer accurately reflected reality. And so for that reason, his model was rejected, and the King of France actually had to die of smallpox before the French people would pick up inoculation. So the conclusion of my 11th grade project was that mathematical models are powerful. They have the ability to simplify reality, but that they come with limits. They are, at the end of the day, only these abstract generalizations. So it would be dangerous to use them as replacements for thinking. Instead, we should use them as a supplement to our thinking. And this brings me to my 12th grade EI project, which is also about mathematical modeling and epidemiological models, but in a slightly different context. And the focus of my 12th grade EI surrounded the utility of mathematics, which is this ability that math has to describe two seemingly different things in reality's terms using the same or very similar math. And the two different things that I wanted to describe or see if they were similar using math were mathematical models that are used to predict the spread of viruses, which I studied last year, and then mathematical models that are used to predict the spread of rumors. And so throughout my 12th grade, I wanted to get a look at whether or not similarities existed between the math that was created to explain both of these phenomena. And the first step that I had to take toward answering this question was finding two models to compare. The first I already had from my 11th grade year, that would be Bernoulli's work, but the second would have to be a rumor spread model. And I decided to heavily reference the rumor spread model made by two mathematicians, Dale J. Daly and David G. Kendall, that they created in 1964, used to predict the spread of rumors. And so after studying these two models, it was time to make connections. And I find that the best way to describe these connections is by using visuals. So I've created a video that we can watch to understand them.
So we've made it to the part of Yara's AI presentation comparing Bernoulli's epidemiological model to Daly and Kendall's rumor spread model. Congrats! To understand these models, let's first compare how viruses and rumors spread at the simplest level. Let's start with viruses. A virus-infected population can be split into three groups: the susceptibles, those without the virus, which we will denote with white circles, the infecteds, those with and spreading the virus, denoted with green circles, and recovereds, those who have recovered or passed away due to the virus, denoted with red circles. Imagine these three groups, represented by their respective colored circles, randomly bouncing around in a box. If a white circle touches a green one, it turns green, just like a susceptible person becoming infected. Over time, green circles can turn red, representing recovery or death. The purpose of Bernoulli's model is to define the probabilities of these different interactions between populations, or circles, happening over time. Now, let's switch to rumor spread. A rumor-stricken population follows a similar structure to viruses. There's the susceptible population, people unaware of the rumor, the infected population, those who know and spread the rumor, and the recovered population, those who know the rumor but stop spreading it. We'll use the same colors as before to denote each population. Let's cue the animation to visualize this one. At first, if a green meets a white, the white turns green, just like virus transmission. But green circles becoming red is where rumors differ from viruses. Daly and Kendall assume that if two green circles meet, they both turn red. It's like two rumor spreaders exchanging the same information, deciding it's old news, and not spreading it, becoming recovered. Daly and Kendall also assume that a green circle will turn red after hitting a red for the same reason. So we've covered how rumors and viruses spread in Bernoulli's and Daly and Kendall's model. Now, what are the major similarities and differences? Both models account for the same three populations: susceptibles, infecteds, and recovereds. They also both use very similar mathematical functions to describe interactions between different populations, like differentials. The biggest difference? How people become recovered. In Bernoulli's model, recovery happens over time and at random, while in Daly and Kendall's model, it depends on interactions, when rumor spreaders meet each other or are recovered. Thanks for watching, sending this back to Yara in real time.
So I hope that video helped improve your understanding of the virus and rumor spread model. And the greatest takeaway is that both rumor and virus spread can be described using the susceptible, infected, recovered model, or the SIR model. And whenever I show this video, I always like to give credit to Mr. Nauman, a teacher in our technology department, who helped me write the code to the animation. And also Caroline Bailey, she graduated a couple years ago. Her EI was about the spread of COVID-19. And so I was also able to take some inspiration from her work. Okay, so I did the research and now it was time to create some of my own work. And if you try to remember that animation you saw in the video earlier, my model is, oh, and excuse me, let me quickly explain that I was trying to create my own take on a rumor spread model inspired by the math that I saw in Bernoulli's work and in Daly and Kendall's work. So continuing what I was saying, my model is a code that performs that animation that you saw in the video 100 times, but with 49 white circles or susceptibles and 1 green circle or infected. And then I tell this code to stop each run of the animation when the number of green circles hits 0, or in other words, when the rumor dies. And so what you see on the screen is a part of that code. It's the section that calculates the probability of each type of interaction between the 3 populations happening within the system. And it's from these probabilities, that the code decides which members of which population meet and at what time in the model. Okay, sorry. And then I also told this code to graph the results. And these are the results. And what this graph is telling you is that in a group of 50 people where one starts with a rumor, out of 100 trials of that scenario, most of them will end with about 10 people never having heard the rumor. And there were some outliers. So here you'll see that one of the 100 trials ended super early. The rumor died super early with about 40 susceptibles left. But after running the simulation about 100 times, we start to see a pretty clear average. And the more times you continue to run this simulation, so say I were to do this like 1,000 times, the bigger pattern that we would begin to see. And so this brings me to the conclusions of my presentation. The first being that simplifying the spread of rumors and viruses down to their mathematical forms, they are fundamentally similar. They can both be described using the SIR structure. So we do get a glimpse at mass utility. And the second conclusion that I came to is that mathematics is worth understanding. And this is a conclusion pretty similar to the one from my 11th grade project. Math has a really unique ability to simplify the complexity of reality. And it's so critical to have a good grasp on it because it could maybe simplify your life too in some sort of scenario. So yeah, that marks the end of my joint 11th, 12th EI project.